Uh, Hello everyone. In the last lecture, we learned about white box testing method for deep neural networks, which was clearly different from the white box method for traditional softwares. So in this lecture, we will continue to learn about the white box approach for testing deep neural networks. So as I said in the last lectures, DNN testing techniques have recently emerged as an important research topic in the field of software engineering. But these techniques are still at early stage, so there exists a lot of rooms for us to enhance the effectiveness of DNN testings. So anyway, let's start with this week's lectures. Today, I will quickly review about the main goals of the deep neural network testing and the key idea of the white box testing for DNNs. And then I will introduce the main challenge in the white box testing method for DNNs, although this challenge is not a well-established problem like the path explosion problem or symbolic experience. And then we will learn about the existing techniques for mitigating and resolving these challenges. More concretely, we will explore namely neuron selection strategies. Lastly, I will introduce one of the state-of-the-art techniques of white box testing for DNNs called ADAPT. And actually, this paper was selected as the best paper at ISTA 2020 last year. And I will introduce it in detail because I participated was a co-author for these papers. Okay, let's start with the general goal of the DNN testing. So as we discussed in the last lectures, the goal of DNN testing is to generate input vectors that are likely to maximize a given coverage metric, such as neuron coverage or top K neuron coverages, where these are specialized for testing DNNs. And the hypothesis is that if we succeed in increasing a given coverage metrics, we'll be able to find many adversarial inputs that triggers the incorrect behavior of DNNs. So actually, this input on the right are actually found by DNN testing tool ADAPT. So the original label of this image was Pomeranian. But as these two images on the right are mutated, and if we look closely, we can see that they are slightly different from the image on the left. But it looks almost the same image to me. And these two adversary images were labeled by the realistic DNN models like VGG and LesNet as cowboy hat and spider monkey respectively. So to our eyes, these two images on the right should definitely labeled as the Pomeranian, not cowboy hat and not spider monkey at the bottom image as well. So personally, this real-world DNN model still seems to be unstable for using at the safety critical domains. And so to sum up, the ultimate goal of the DNN testing is to find such adversarial input as much as possible in the limited testing budget by maximizing a given coverage metric such as neuron coverages. And to achieve this goal, the white box testing methods usually use the gradients of the internal neurons. More specifically, as we learned at the last lectures, the simplified white box testing methods for DNNs consist of 3 steps. First, it selects some neurons for the gradient calculations. And in these pictures, suppose that we choose the 2 neurons highlighted in green at the second layers. And the second step is to calculate their gradient of the selected 2 neurons. And lastly, we simply add their gradients to the original input in the direction of increasing their output values, thereby increasing the number of activated neurons. And here is the very simple question. So what is the most important part among these three steps? Yes, as you can see, the first step, which is the neuron selection, is the critical part of white box testing method for DNNs. So namely, neuron selection strategy answer the following questions. Which neuron should we first select for the gradient calculations? And first thing that comes to mind is that it is possible to simply select any neurons in order or sequentially, or select all neurons and add their gradients into the original images. But however, when testing real-world DNN models, we must face the following key challenges. First, these models like VGG19 and ResNet 50 have so many candidate neurons that it is difficult to choose. For example, ResNet 50 has about 94,000 neurons. And second, during the DNN testing, we are not able to select the large number of neurons for the gradient calculations, as we should change the original image slightly, not much. So as you can see in the left mutated images, the implicit goal of DNN testing is to find adversary images that are nearly identical to the original images, but classify them by different labels like cowboy hat. That is, if a lot of gradients are added to the original image by selecting too many neurons as shown in the figure on the right, the mutated image can be meaningless. So in other words, we have to find many adversary images by carefully choosing a few neurons among the tens of thousands candidate neurons. So this is the two challenges. And more fundamental challenge is that we do not know clearly which neurons affect the value of the output layers. So consider the mechanism of how DNN model layers. It simply calculates the output value of each layer starting from the input vectors sequentially and returns the label with the highest value of the output layers. So in this case, since the output value corresponding to the Pomeranian is higher as 0.5, so it will be labeled correctly in this case. So in other words, in terms of generating an adversarial input, the output value of the Pomeranian should be decreased and the value of cowboy hat should be increased. But here is the problem. So at this time, we do not clearly whether to select, for example, green neurons or red neurons to increase the output value of the cowboy hat at the output layers. So these three reasons make the neuron selection non-trivial when testing real-world DNN models. And to address these challenges in white box DNN testing, diverse, namely neuron selection strategies such as DeepExplore, DLPHOS, DeepHOS, and ADAPT have been proposed. Like the top research topic about coverage metrics for DNN testing, these neuron selection strategy are also actively ongoing research topics. So each neuron selection strategy has its own criteria to pick some neurons first. And so first, let me introduce the neuron selection criteria used in the two techniques, DeepExplore and DLPHOS. The first technique, Deep Explorer, is to randomly select the K neurons that have never been activated during the DNN testing. So suppose that the value of the K is 2 and the blue neurons have been activated at least once and the green ones have never activated before. So Deep Explorer is to simply and randomly select the 2 neurons among the green ones and calculate the gradient of the 2 neurons and add their gradient to the original inputs. And after executing the DNN model with this newly generated input, Deep Explorer checks whether the green ones are activated or not. And then among the remaining green neurons, in this case 4 green neurons, and these are inactivated yet, this technique repeats the neuron selection process until the testing budget expires. And the next technique called the DLPHOS have presented 4 different neuron selection strategies. So each strategy of DLPHOS is also very intuitive and simple. So let's look at each strategies. The first strategy is to select K neurons activated frequently. So suppose that this number in each neuron denotes the number of activated times during the DNN testing so far. So when the K is 2, for example, this strategy will select the 2 neurons in the 3rd layer that are most frequently activated. Conversely, the second strategy is to select the K neurons activated rarely. Using the second selection criterion, these red neurons that have not yet been activated or have been activated only once will be selected. So the intuition of these first 2 strategies is that the neurons covered frequently or rarely perhaps are more possible to introduce the defect or result in unusual logic in the DNN models. And the third strategy is to select K neurons having the top weight. And to calculate the weight of each neurons, we just add up all the weight in the preceding layer associated with each neurons. So for example, the weight of the neuron B2 N2 is calculated by adding just weight 1 and weight 2 and weight 3. So after calculating the weight of all neurons, and this strategy simply picked 2 neurons highlighted in blue in this case. And the intuition of this strategy is that the neurons with the top weights maybe have a large influence on the other neurons. I think this expectation also seems to be reasonable. And the last strategy is to select the K neurons near the activation threshold setup. So suppose that K is 2 and the threshold theta is 0.5 and the output value of each neuron is as follows. And it is so easy question. So which 2 neurons will this strategy choose? I will give 5 seconds. Yes, this strategy will choose the 2 blue neurons which are closest to the threshold value 0.5. And in this paper, DLPHOS, the experiment results show that DLPHOS was better than Deep Explorer in terms of increasing neuron coverages across the 2 different deep neural network models, LeNet4 and VGG16. And for example, when testing VGG16, the first strategy, which considered the number of activated times of each neurons, succeeded in improving the neuron coverage by about 6% compared to Deep Explorer. Okay, the next neuron selection strategy called ADAPT is actually our papers. And this technique is the state-of-the-art neuron selection strategy for white box DNN testing presented in ISTAT 2020. And we also received the ACM Distinguished Paper Award last year. Actually, it is similar to my ICSI 2000 papers introduced in the previous lectures. So it will not be difficult to understand this new technique ADAPT. So let's start with the motivation of these papers.